Okay. Okay. So welcome everybody. So as mentioned, my name is Craig Hennessey. Just before we begin, please ask questions as we go. So I have a chat window up, and so as I go through this hopefully will be quite interactive. I'm going to go through sort of the use of eye tracking and how to use eye tracking. If anything is of any interest or you have a question about any point, just put it in the chat window. I'll keep an eye on that and then answer it as we go. Don't save it to the end because we're going to cover a lot of material and might be hard to get back to it. Okay, so I did my my undergrad at SFU here in Vancouver, which is Andrew Dukowski's former school. Then I did my master's and PhD at UBC, studying eye tracking systems. And Andrew was actually on my PhD thesis committee. So it's a small eye tracking world. After that, I've still got some affiliations with UBC, some at BCIT, and then I co-founded Gazepoint, which commercializes eye tracking systems and related peripherals. So in this talk, I kind of split it up into what do you do as a researcher? Well, you're investigating or researching some question. The why you are looking at something. So this is not what we're going to talk about. Andrew actually broke this down into two nice categories of diagnostic and control. Most of our clients or customers are in the diagnostic field. So they're looking at usability. That could be websites, it could be software. They're looking at market research. So it could be advertising, print media, commercials, TV commercials. And then they're looking at various research topics like dyslexia, various medical conditions, and so on. So that's our primary use case. The other use of eye tracking is in control. So you're actually controlling something with the movement of your eyes. And I'll just make a sidebar that Microsoft Windows actually has integrated eye tracking into Windows itself. So it used to be you had to have a niche tool to do it, but if you actually just press the start button and type eye, up will come eye control, and it's actually quite good. So it's an accessibility feature for those who have limited mobility. You can actually use your eyes to interact with Windows now, and it's built into the latest kind of releases of Windows 10. Okay, but we're not going to talk about that. What we're going to talk about is where you're looking and what you are looking at. So where you are looking is everything to do with the hardware, the participants, the images that are captured, the calculations on those images to compute the point on the screen that you're actually looking at. So that's the where. And then the follow-up is, okay, I know where you're looking on the screen. What is on the screen where you're looking? So for a human, it's very easy to say, oh yeah, of course I was looking there. But for your analysis, for your data analysis, you need to know what was on that screen. And for a static image, that's maybe not too complicated, but you've got different screen sizes, screen resolutions, and then you've of course got dynamic content. So you might have a video playing, and so you need to see what content was at that location when the user was looking at that. There's web content where you can scroll. There's mobile device content, and so there's a lot that goes into saying, okay, what was on the screen at that point when you were looking on the screen, and then at the very end we'll kind of touch on, okay, you've now got this data set, you've got the gaze, you've got the content you were looking at. How do you analyze that? And so we'll look at areas of interest, different visualizations, fixation maps, heat maps. And that sort of leads into the why are you doing this? And I will leave that for you. You have a wide range of research topics. And so this is sort of the lower level stuff of getting the data to answer your research question. So that is the goal of this talk. Don't know how to do a poll in this, but I'd like to know how familiar people are with eye tracking. I seem to recall reading that it was a range. So some people have no familiarity. There's probably a few experts, and I'll just assume that's the case. So we'll cover every bit of detail that I can cover. So let's start with the eye tracking equipment. So what is an eye tracker? It's a little piece of hardware. I've got one right here. Take this off. They're all going to look about the same. For the modern ones, they're non-contact, so there's nothing touching your face. They're remote, which means they're in the distance. Again, nothing touching your face. There's no bite bar or chin rest. Some of the older researchers might remember the bite bars and chin rests. There was very limited field of view in the past, and so you really had to lock down the subjects in order to get their eyes tracked well. So the modern systems, they're camera-based, image-based, remote, and they're taking pictures of your face, and that's how they track the gaze. So pretty much all systems are like that at this point. The head-mounted is a different topic. So this is non-contact remote, and then single camera. There are multi-camera systems, more for maybe cockpit environments, or maybe a full driving simulation where you have the ability to look out the window of the car, and so you need to be able to track the movement of that. But the majority of eye trackers are a single camera in front of a display. Update rate. So these are camera-based systems, and so your update rate is typically aligned to the speed of the camera. So the cameras have a certain number of images per second they capture, and the most common rate is around 60 hertz or 60 frames per second. And the reason for that is the eyes are very fast. The movement of the eyes are incredibly fast. And in order to capture most of the dynamics of that, you need a minimum of 60 hertz. And so 60 hertz is 16 milliseconds per frame. So at 16 milliseconds, you're catching most of the dynamics. That's at 60 hertz. Many companies also have a higher performance system. So we have a 60 hertz system and we have a 150 hertz system. At 150 hertz, you're tracking faster. We're now down to 6 milliseconds per frame. So you're going 2 and a bit times faster. What do you get for that increased speed? Well, you've got that much faster data throughput, which means you've got that much faster processing requirements, that much faster data aggregation and collection. And so your computer needs to be able to handle that. You need a higher powered machine to run it at the higher speed. You capture a little bit more of the dynamics of the eye, but not into the next level. So the movement of the eye on the screen, where you look at something, you fixate on it, and then you mentally have another thing you want to look at, and so the eye jumps to the next spot. The dynamics at the next level, you need something on the order of 500 hertz. So there's a few more sort of niche specialty systems that do the much higher frame rates, 500 hertz, 1,000 hertz. And those systems can track the microsaccades and the tiny little jitter of the eye. And so those are used for very niche, like neurological studies on the behavior of the eye itself. And that's really not what most people are interested in. Most people are interested in this, something on the screen. Where are you looking? Are you looking at it? How long did it take you to notice it? And things like that. So 60 hertz is a good number for almost all cases. 150 hertz, so the kind of the model up is a little bit better for speed. What I'll show you here. So there is one benefit that we know for the higher frame rate though, and that's when you have children or participants who don't sit very still. So we've had a number of clients who study children, and in particular children with ADHD. And these are kids who are fidgeting quite a bit. So right now we're looking at the system at 60 hertz, and it's tracking, and it loses my eye if I move my head fairly quickly, but it's locked on pretty well. But if I'm sort of a little more shaky, you can see that the tracking, it's still good, and the data is going to be, you're just going to have dropouts, but it'll more or less, the data will be there. But for kids who are shaking quite a bit, 60 hertz might not be enough. And so you actually might want the 150 hertz. And now it's tracking my head as, even though I'm kind of shaking around a lot more. So that's the one use case where we feel that the one higher speed up is particularly useful over the 60. It does take a little more CPU power. So that tracks the movement. The other specs, so these are kind of like the specs you'd see on your eye tracker sales sheet when you're trying to pick a unit. So you definitely want non-contact, 60 hertz kind of minimum. Head box. So the head box is how much can the subject move while still being tracked. And there's two parameters to that. There's field of view and there's depth of focus. Now, often, on a little blurb of specs, there's only so much people can put in. So the head box, it's actually like a frustrum. So the camera field of view is actually like a cone kind of shape. You'll often see it as an XYZ kind of number. It'll be narrower, closer to the display, and then it expands out. But what does that look like visually? So here we have our field of view. So field of view being our X and Y. And this little marker here at the top is our sort of depth indicator. And so there's a depth of focus as well. So field of view is obvious. It's how much can you move left and right and up and down. And then depth of focus is the in and out. And if you can see the little features of my eye, they're still sharp. And as I get to my sort of close range, they're still sharp. And as I keep going, you can see them start to blur, and then it starts to lose the features that we're trying to track. So there's a depth of focus, which is set by the lens and set by the manufacturer. So you've got a minimum in and then a minimum out. You can see that I've kind of blurred out my image features on the far side. So you've typically got somewhere around 20 to 30 centimeters in depth, and you've got 20 to 30 centimeters in X, and usually sort of a little bit less in Y, just because the cameras are they're not rectangular, they're a little more wide and tall. And then you've got your depth of focus. So we have two systems. We have an SD system, which is a lower resolution system. So it's enough to track the eyes, but you don't have a huge amount of head movement. The higher cost system, which is the one I'm showing, has a larger field of view. So we quite like the larger field of view. You really want your participants to not have to sit in a narrower range. You don't want to lose data just because they shifted their head a little bit. But that one is one that you can kind of trade off on the cost. Range of motion, depth of focus. Any questions so far? Accuracy. So pretty much every system will spec something between 0.5 and 1 degree of visual angle. And so what does that mean in terms of accuracy? What you kind of want is accuracy in terms of pixels, but what does a degree of visual angle mean? It means that your eye is out here, out in space, and it's looking at the display, and most are designed at a standard standard viewing depth, which is around 65 centimeters. So I think I'm a little figure here. So you've got your display and roughly 60 to 65 centimeters distance from the display. So if your eye's out here, 1 degree, so if you take a cone that's got 1 degree in diameter and project that out onto the display, that's what's kind of meant by 1 degree of visual angle. That is still hard to understand. And so what might make more sense is if you actually run the math, it's sort of about the size of your thumb on the computer screen, or about 1 centimeter on the screen. And so some people, when they first get into eye tracking, they kind of think that the eye tracker is going to output data like a computer mouse, right? Here's my computer mouse, and I'm currently looking at the E, and so now the cursor's on the E, and now I'm looking at the Q, and it's on the Q, and now it's on the head, and it's looking at the head. That's not how eyes work. They don't point at a point and just sit there. They're always a little bit of jitter. They're jumping around, looking at different things. And in fact, the fovea, which is the high resolution portion of your eye, so you've got your retina, which is the back surface. There's a small patch that's the high resolution. That patch is also not a point. That patch, any features in the field of view that land on that patch are seen in a sharp, crisp fashion. And so your eyes don't need to point more accurately than sort of the size of your fovea. And so you're not really going to get better than about sort of 1 centimeter or your kind of thumb on the screen in terms of accuracy. Actually, let me just do a quick calibration, and we'll just check that. Okay, so if I turn on my little gaze pointer here, I've just slaved the cursor to my eye. So I'm looking at the E, and you can see that, there's a little bit of bounce, and there's a little offset, head box. I'm looking at the head. So you can't expect pixel accuracy. That's what a mouse does, but certainly not the eyes. So most modern systems have pretty good accuracy at this point. They'll spec it as 1 number, but it does also vary across the screen. So you do your calibration, and the top corners of the screen might have lower accuracy than perhaps the middle, or the calibration points might have the best accuracy, and the further you get from the calibration points, there might be a slight increase. So this is sort of the average error. Okay, so that's the eye tracker. Let's look at how do you stick that in front of your display. So there's a variety of ways of doing it, and it's extremely important that you do it right, or do it well, because the quality of your data does depend on how well you set up the system. So what I have on my setup here, cables. So I've got a tripod setup. So we have a tripod, best amount and laptop mount setups. So I'm using a tripod because on my desk, my screen is sort of this far up from my desk. And what you want is you want the eye tracker exactly at the bottom of your screen. In fact, you want it in front of the bezel. Greg's eye view. The webcam at my eye. So it's at my eye. Can you see that the tip of this is actually right lined up with the bezel of the screen? So it's actually overlapping the bezel, and not the screen itself, but the bezel of the screen it's right on that line. I don't know if I can see that. Something like that, yeah. What that does is it gets you the most screen real estate for the least eye rotation. And so this is a feature that's very important. You can see my eyes. They're being tracked nicely, and we'll talk more about that soon. But as I, let's say, start looking up and up and up, you can see, I'll pause it, I've lost the glints in my eye. So as my eyes rotate, features get lost. And so you want the eye tracker as close to the bottom of the screen as you can, which makes the top of the screen as close to the system as possible. So for my setup, and I go through a lot of eye trackers, we use a tripod. Another mount is what we call a laptop mount. So this is a mount that you would put on the keyboard of your laptop, and it's as low profile as we can get it. Some systems are a little slimmer, but at any rate, you want it to mount as tight to the screen as you can, and just underneath, or just even in front of the bezel. So that's another mount. If I were to use this mount on my computer, on my desk here, there'd be a gap of this between the top of the eye tracker and the screen, and that would not be a good feature. So it's a little thing, but it does affect the quality of your data. And then the last mount that we have, and different companies will have different solutions to this, but we have what we call a VESA mount. So on computer screens, and this used to be very common, there's 4 holes in the back of your screen. And those are known as the VESA mount pattern. And there was 2 sizes. There's 75 millimeters displacements, and there is 100 millimeter displacement. And now they make screens without them at all. So our solution is this little mounting bracket. So there's a bracket, and put in your eye tracker like that, one for each side. Missing one of the arms. So this goes to the back of the screen, mounts to the screen, and then the eye tracker can be located, again, directly in front of the bezel of the display. Some companies have a magnet that you stick to the screen, and then you can stick the eye tracker to it. So you stick the magnet on the bezel, and then you stick the eye tracker to that. It's got a magnet in it as well. So those are all mechanisms for getting the eye tracker at the best possible location below the screen. And note I said below the screen. You cannot put it above the screen. We've had clients who tried that and said, it's not working. And no, eye trackers don't work above the screen. Let's see if I can demonstrate that. So right now you can see, you can see my upper eyelid, my lower eyelid, everything looks good. I've got a nice shot of the eye. What happens, cables are long enough. Yeah, that's kind of roughly at the top of the screen. Look at the image now. Look where the glint is. So I'm looking at my eye, and you can see that the glint It's disappearing every once in a while. And what the heck is that? Well, human eyelids and eyelashes tend to angle downwards. And so if you try to put the eye tracker above the screen, you run into the issue of eyelashes and eyelids occluding the features of interest, the pupils and glints of the eye. So it should be below the screen, quite close to the bottom as possible. So tripod, that's the laptop. And then the final thing that we can talk about, if we have enough time, is this little setup here. So here we have a mobile device test stand. So we have an eye tracker, we have the mobile display. When you have a mobile phone in your hands, it's much closer to you than your computer screen. So the mobile phone is closer to you, and you poke at it, which you don't generally do with your computer screen. So the stand, and we'll get to that later, but the stand provides a mechanism for holding the phone where you can also kind of put your hands on it as well, and so that you can type on the screen, but you don't occlude the eye tracker with your hands. And then I included it in this section, which is the biometrics. So we recently added on. So when we design things and create products, we really just listen to the customers and they tell us what they want. And we had customers saying, well, can we integrate your eye tracking with other biometrics, in particular galvanic skin response? So sorry, like some audience participation. Has anyone used GSR? It's also known as EDA, electrodermal activity. It's the skin response of your fingers. So yeah, I'd say that that's probably the most popular biometric signal that people want in addition to eye tracking, next to EEG. So EEG is also a very popular biometric signal. And so eventually we said, okay, well, let's just make a system. So it looks like, where's it there? This. So we have a little box that does the signal processing. And then we have a little module that you can stick your fingers in. And if you stick your fingers in it, we have now the skin response. So this is GSR measured in kiloohms. The other units of interest are microsiemens. And a microsiemen is a siemen is 1/ohm, and a micro is just 1/1000th. So you take this number, invert it, and multiply by 100,000. So that is skin response. And so for those of you maybe not familiar with skin response, the pores in your skin open and close based on a variety of reasons. Exercise, so if you're hot, you need to cool down, your pores will open and sweat will come out as a cooling mechanism. But they're also related to stress. If you're stressed, you get nervous, you start to sweat a little bit. And by a little bit, it means undetectably, like you would not notice. So just tiny, tiny amounts of moisture that leave your skin. This is actually the same measure used in lie detectors. So if you've seen those cop shows, when they do the lie detector test, they strap up the fingers and they're looking at this number here, and then they start grilling you with questions to see if you're lying or not. Whether that works or not is, I think, debated. But anyway, this gives you a measure of we'll call it emotional response. So, or it's a biometric signal. It's a signal that you can collect that the user does not have to actively report. And then since we had something stuck to your fingers anyways, we thought, well, let's just throw on an LED. Some of you have smartwatches that have a green light in it. And so that measures the pulse of your heart. So as the blood flows through your extremities, when the light's shining in the skin, shining through the skin, a pulse will change the intensity of that signal, and we can record that with a photo detector. So that's biometrics. Let me make sure I covered everything there. Yeah. Okay, and so that's, in this case, it's because we make the eye tracker and we make the biometrics, they kind of go together nicely. Oh, should maybe mention the third signal, this dial. So the dial is literally a dial. So we have a dial, and you can rotate the dial. And you might say, well, what do you use a dial for? It's for dial testing. What is dial testing? Well, when you do, let's say you have somebody watching a commercial and you want to know how emotionally effective it is, you could let them watch the commercial, and at the end of the commercial say, well, what part made you sad? What part made you, or what part gave you the most emotional response? And then they have to think back and remember. With the dial, you can simply say, keep your hand on the dial, and as you get more angry about the commercial, go up, and as you get less angry, go down, or as you get more interested in the product, go up and down. So it's an analog measure of engagement. Yeah. So there's a whole body of science around lie detection. So one of the things is some people look up. So they look up when they're lying, or look to the left, or they look to the right. And then they've got the sweat response as well. So yes, there's a lot. It'd be really interesting to see someone use these modern tools to really dig into lie detection. I think it's at least been proven in the past that it's not reliable, and so can't be used in the court of law. Doesn't mean it's still not used, at least in police shows. Okay, so that's kind of a little overview of equipment. Now we've got research participants. So we've got our equipment, we've set it up perfectly. Now we're going to get people to sit down in front of it. And, like a computer mouse, you'd expect it to work exactly the same for everybody. You go left, it goes left, you go right, it goes right, up and down, and you can move your cursor just with your eyes. Well, that's not actually how it goes. Every person is different. Every person is unique, and some will track better than others. So now I'll cover kind of some of the common issues that you'll see, and some solutions for it. So let's start with glasses, because this is probably the most common problem you'll see with eye tracking. So you've got your eye tracker up, you put on a pair of glasses, and then the system's not tracking. So why is it not tracking? Well, eye tracking systems are almost all based on a camera and infrared light. So the face that you're seeing here is not visible light. That's actually infrared light to make it insensitive to ambient light. So whether the room lights are on or off, you don't want your system flashing lights at you. And so we use infrared light that the user can't see. Because the system now is generating the light, if you put a pair of reflective glasses in front, then you can see that those reflections can bounce off the glass and then come back in the camera and cause problems. So, most of the time here it's tracking fine. You can see that there's some reflections off the frames. Those don't seem to matter because my eyes, if the frames are blocking my eye, then my eye can't see the screen. So, okay, that's fair. But it's these little white ones here that are problematic. And you can see that, as long as they're not on my eye, it's fine. But once they hit my eye, hits the features I'm trying to track, well, then we can't track it anymore. You've kind of corrupted the image, and there's nothing the system can do to overcome that. So how do we deal with that? This is where you, the experimenter, needs to understand that is an issue, and for this particular client, we need to make an adjustment. And so what we heavily suggest is that you always use a chair that's pneumatic, so you can make it higher or lower without much effort. So if I raise my pneumatic chair up, wow, where'd that glue go? The reflections are gone. Oh, they're still there, they're just lower. So by raising my height up, I'm now looking down a bit more. And if I have a quasi standing desk, so I'm gonna just, so raise the subject up and then rotate the eye tracker up to point towards the subject again. So I'm gonna do that as well. So I'm gonna rotate to get my head centered. And now there's very little overlap. I have to really kind of look down and into the eye tracker in order to get those to overlap my eye. So that's sort of the best you can do when the glasses are reflecting back into the eye tracker. So raise the subject up and tilt the eye tracker up, and that solves it. Now, not every company will show you this image. Some eye trackers will just give you a green or red marker that says green good tracking, red bad tracking. Here you can kind of see why it's bad tracking, why it's unable to track. And that gives you a little bit more feedback. But if you do have glasses, we suggest bring the subject up, tilt the eye tracker up, and that gives you your best possible response. These are pretty standard glasses. They are a little bit shiny. The frames are reflective. Some people have plastic frames, and so they might be smoother, rounder, and so they might not have as much reflections. You might have big horn rim glasses that have quite a bit of features on them. Those might cause more trouble. So in general, most glasses can be accommodated by just proper placement of the participant and the eye tracker. I'm going to rewind back 1 second to field of view again. When you place the eye tracker, you want to, of course, be centered on the screen, as close to the bottom as you can. And then where do you put the subject? Well, you wouldn't start them at the edge. You start the subject in the middle. Back. And then you want to start them a little high. So here's, okay, so in the depth of focus, you want them sort of this green marker, you want them here as well. Why would we start them just a little high? Wouldn't we want kind of start them in the middle so we have the most range of motion in and out and up and down? Well, in practice, what we found is that when most people are doing a study, they start with sitting up. And depending on the duration of the content they're going to look at, over time, their posture changes and they start to kind of get more comfortable and sag down. And now, because I started kind of up at around 2/3, once I've slouched down and now I'm kind of middle, and now I've got my sort of median range or middle range of head movement. Okay, so that was a sidebar on starting your subject in the field of view. So that was glasses. Contact lenses are also very commonly worn. And there's two kinds of contact lenses. There's hard and soft. Does anybody here wear hard contact lenses? My guess is no. Silence. So no one has hard contact lenses. I imagine a number of you have never even heard of hard contact lenses. Nor had I. However, they're actually very common and popular in Asia. So it seems like in North America, Europe, contact lenses are the soft, kind of the gooey, disposable contact lenses. But in certain locations around the world, hard glass contact lenses are more common. We found that with the soft contact lenses, they look just like your normal eye, and so they have no effect in eye tracking. With the hard contact lenses, they're fine as well, except when you blink. When you blink with the hard contact lenses, it shifts them in the eye, and when you open it up, they reseat back onto the cornea. And so for a fraction of a second, there's some weird movement of the eye, this smooth surface where the light is reflecting off, that it has a bit of trouble tracking, or there'll be some movement between there. So fine for most glasses, fine for soft contact lenses. Be aware that hard contact lenses may have some artifacts, but in general, I think they're fine as well. Okay, so that's glasses, contacts. Age. Aged is surprisingly problematic. You know, most of us are kind of university aged, working at university, but a lot of studies involve infants or children and elderly. And so those two age groups have particular issues or things to be aware of. For the youth, it is that the pupils are extra bright. So if you look at this image, and you can look at my eyes, and my eyes are actually white. So my pupils are white. If you saw me in the real world, my pupils would actually be black, just like everybody else's. But the way the eye trackers work is we're actually shining light into the eye that hits the retina, the back surface of the eye, and then coming back out exactly along the same axis as the light came in and striking the camera. And so you get a bright pupils. It's what's known as the bright pupil effect. It's the principle is retroreflectivity of the retina. If you've ever driven in a car at night and you see your headlights shine in a cat's eyes again have that really strong retroreflective property. So infants have a stronger response, and so their eyes might be extra bright. If they're extra bright, the system needs to handle that range of intensities. We have sort of a default setting that can kind of go from no eyes to eyes quite quickly. But if the eyes are not within a kind of common range, in our system, we have a gain sweep. So if it can't find the eyes for long enough, let me turn the gain sweep on. Then it starts, you can almost see it a little bit, cycling through the full range of gain, so that when the eyes finally do come in, and if they're extra bright, when the gain is low, they'll be in the field, they'll be in the range, and then it can lock on. So that's if the eyes are too bright, and that can happen with children and younger. And then in the elderly, sort of the opposite happens. As you get older, your eyes age, and in particular your lenses. So the lens in your eye starts to fog a little. And again, this varies between all subjects. So some people's eyes are going to be perfect, and some are not going to be perfect. And so as your eye fogs, this is actually known as cataracts. So as the lens fogs, the light that's coming in, hitting the retina, coming back out, dims. And so you end up with a dimmer and dimmer pupil, retroreflective response. And so that's also an issue. And again, our gain sweep can help kind of lock onto that and then get the gain right. But in both cases, there's something you can do as the experimenter. So you can manipulate the ambient environment a little bit to help the system out. So if it's an older subject, what you can do is you can make sure that the room in which you're doing it is not very bright. And what does that do? Well, the pupils, the iris, which is the muscles that control the size of the pupil is just a hole in the eye. So the iris is the thing that controls the eye. So again, if you're going to do a study with elderly, you have this image, you see their face. If it's not being tracked because the pupils are tiny or very dim, try dimming the lights in the environment. Okay, we'll get to that in a sec. Dim the environment, and that will make the pupils dilate, or the iris to open. That allows more light in, and you'll get a better response. So the ambient light can be used to kind of tweak the size of the pupils a little bit, and they'll get bigger. I can demonstrate that here by closing my eyes. So right now my eyes are in the dark, and when I open them, they're going to be very large because they're trying to collect as much light as they can. They're going to quickly realize there's lots of light, and so then they're going to shrink. So you're only going to see this for a quick fraction of a second, but you saw the size of those pupils when there was less light, and then they constrict to the correct ambience. I can do a quick demo again. You can see they got really big, and then they shrink down. So if they have dim pupils, you can dim the lights. If they have really bright pupils, like children, you can make the ambient environment a little bit brighter. So turn up the lights a little bit, and their pupils will constrict somewhat, and then get a bit dimmer. In terms of colored pattern contact lenses, that's an excellent question. Nowadays, you can buy cosmetic contact lenses that are colored. So I haven't experienced those in a participant. I have seen them. I would imagine that they don't occlude the pupil, so the hole in the eye, because then you wouldn't be able to see through them. So as long as that is still open, you've got a pupil. And then the glint here, the white dot, is off the surface of the lens. And so these contact lenses, they're smooth. And so as long as you still have the pupil and the glint, it should work. One interesting feature is in infrared, the colored lenses might not be colored anymore. In fact, they might even be see-through. Many inks and dyes are not visible in infrared, or infrared won't they won't show up in infrared. So I don't know, can't quite see it, but my shirt has some stripe patterns and it's blue. But you can see the stripe pattern. Of course, you can't see blue because it's in infrared. But sometimes, I'll be wearing a shirt with a pattern, and the pattern won't be visible because that dye or ink is not visible in infrared. Okay, so that's youth and elderly. Jewelry and cosmetics. Most earrings are fine, so the system's kind of looking for eye-shaped things, and so things down here are not going to fit into that model. A nose ring can cause trouble, so if you've got a ring in the nose that's sparkly and kind of has some response that may look eye-like, that could be an issue. Most objects do not behave like this retroreflective property of the eye. So I will show you. You can see here I have a dark pupil, and here I have a bright pupil. So we're using both of these image features to track the eyes. A nose ring will look the same in both images, and so it gets thrown out. But there's a wide range of possible kinds of jewelry that people can wear. And so you might find that some of them might be causing trouble. And this is where you, the experimenter, you look at this image and you say, is it tracking the eyes? Well, great, okay, good, move on. If it's not, it's jumping to weird things, over the face, then that participant, maybe they can remove it, or maybe that participant, if they won't, then that might not be a subject you're able to use. Most cosmetics are fine. I've only once seen sparkly cosmetic, so something that they were wearing had sparkles in it. I think it was maybe something around the eyes, and had a lot of sparkly material in it, and that caused problems. And so there will be some things that you'll see that will cause the system to be unable to track, and that's just sort of one of those things that you can't make it work for 100% of all possible circumstances. Another face thing you might be wearing frequently, and we see it quite a bit in our customers and their participants, are face masks. So there's a lot of face masks going on right now. As you can see, you put on the face mask. As long as it's not blocking the eyes, should be no problem. I guess, yeah, so if you do that, it'd be problematic. Except if you have the metal band on the outside. So some masks have the metal band here. That sort of behaves like the rim of your glasses. That metal band may have a reflection. That reflection won't be pupil-like, and so should be ignored. So we haven't really seen any problems with the face masks. Certainly the ones where the metal's gone, it's just like a piece of fabric in front of your face. So those are okay. Gender ethnicity. So we haven't seen any difference between male and female. And almost all ethnicities are tracked equally well. I've anecdotally heard that brown eyes might be harder to track than non-brown eyes, but I've not seen that. I've seen all eye colors track equally well. Except I have seen an issue with narrow eyes. So in Asia, where the eyes might be a little bit narrower, I have seen an issue if the eyes are very narrow, the system might have trouble tracking. And now we sell lots of systems into Japan and Korea and China, and they work fine for the most part. But you might run into the odd subject where their eyes are quite narrow, and if they're so narrow that in addition to eyelashes occluding the features that you're trying to track, then the system might not work for that particular subject. Very rare. I mean, if it's too narrow, then you'd have trouble seeing through the pupil, and so that's not a thing. So in general, it should work for all genders, ethnicities, and so on. But that is the one eye feature to be aware of. And we found that it's often the upper eyelid that might be the one that's causing trouble. And so in this case, it's a matter of getting the eye tracker a bit lower, looking up into the eyes. And so you're kind of looking under the eyelids. Question, do you mean double layer mask? I'm not sure what a double layer mask is. These are just the little paper masks. If you had the full face shield on top of that, I'm not quite sure how that would track. Yeah, I'm not sure that would work. And my last topic is medical issues. Again, you're taking a slice of the population, and so there's a wide range of things that can be that the subject can have, and so things like lazy eye, so where one eye tracks well and the other eye is off by a bit. If it's a fixed offset, then the calibration will take care of it. I've once had a subject at a trade show say, I bet the system's not going to work for me. And I'm like, okay, well, let's try it. So he sits down, and when we look at his right pupil, there is a piece missing. So in general, I expect to see a nice white circle. And instead of a circle, there was a chunk missing out of it. And I thought, that's odd. Well, what's wrong with the system? And he's like, no, it's my retina. I'm missing a chunk of my retina. And so there was a piece of his eye missing, and therefore it showed up as a missing piece of here, and the system couldn't accurately track that one individual. So, so the moral of the story is, look at this image. If you see nice pupil and glint, you're good. But there may be issues. There may be these, unique circumstances where somebody has an issue that you maybe can accommodate, and so you can try playing with positioning the system, lighting in the room. But sometimes there's a subject who it's just maybe not going to work for. All right, so we're moving along. You need 5 points to fit an ellipse. Yes, we run our ellipse fitting algorithm over many points, and we try to deal with some occlusion. It's a case where you don't really want to have an if statement for all of these possible situations. You end up with a pretty ugly underlying system. So we try to make it as generic as possible, so it works for 99% of the people. But yes, good point. If you were missing a piece here, you could say, well, don't use these edge pieces here that are not part of the ellipse, but then you need to track that this little chunk missing is an invalid portion. You could look at convexity and concavity and so on, and it gets a little problematic. Okay, participants. So now let's go to the one level higher and look at the tracking, which you've already seen quite a bit of here. I talked about bright pupil tracking and dark pupil tracking. So the eye tracker has lights located near the optical axis of the camera and away from the optical axis. So you got lights in the middle and lights on the sides. The lights in the middle generate the bright pupil. So that's this white looking pupil. And then the dark pupil image is taken with lights on the outside, so the off axis, and that gives us a dark pupil, and it gives us a dual glint. So we actually have two glints here instead of the one glint for the on axis. These are the features we're most interested in to do the point of gaze. So we need the pupil and we need the glints, and we need the dual glints as well. So we need all these features in order to actually do the point of gaze calculations. Field of view, I already covered that in terms of how much head movement you can have. We did touch on how much movement you can do. In general, if my head is doing this, it's okay that I'm not really locked on because the user is not really looking, at something on the screen. This is not a normal way you browse the web. You could get a faster system if you really wanted to track while somebody's doing this. But in general, that for most applications, people, when they're browsing the web or they're doing a study, they're just kind of sitting looking at the screen and their eyes are moving, but they're not moving their heads around wildly. Recovery time, so that's related to the update rate. So the recovery time should be, in this case, 16 milliseconds at 150 hertz. You're down to 6 milliseconds, so 1 frame worth of recovery. And that also counts for blinking. So when you blink, the tracking has been lost, and now it's searching each image and it's trying to find where are the eyes in the image again. Once the eyes become visible, it should immediately lock back onto the eyes. And so you've got a very fast tracking recovery of the participant. Time. Okay, so that's blinking. Talk about participants. Ambient light. So in the environment, because we use infrared, we're less sensitive to ambient light, so lighting in your room, unless you have sunlight. Sunlight has a very large amount of infrared in it. These systems are low power. They run off the USB port. When you have the power of the sun shining through a window, it will just wipe the system out. You just see a white, from a window on this side, you'd see just a white half face, and then you might actually be able to track the other side, but you do not want sunlight. So I highly recommend that when you do your studies, you do them in an interior room, so a room with no window to the outside. Or if you do have a window to the outside, make sure it has blinds that you can close fully. Some people have the metal strip blinds where you pull the divider and they rotate. Those are not very good blinds. They don't shut tight, and they have little holes where the string goes down, and that lets light through. And again, sunlight is so powerful that it can overpower these systems reasonably easily. So you really don't want sun. If you have sun in a window in front of you and the sun's shining on your face, that washes out your face. So that doesn't track very well. If the sun is kind of behind you or elsewhere in the room, maybe it's not on your face, but the ambient light in the room will be quite high, and your pupils will have to accommodate that, and they will shrink. And the smaller and smaller they get, the harder the system has to work to track the eyes in the image. So just in general, you do not want sunlight in the environment. It just makes everything more challenging. Fluorescent light doesn't have infrared. The dark pupil image comes from the off-axis light. So light close to the camera lens comes out, hits the eye, and comes back into the lens. So it's, how do you get it to flip? Eye. Press the eye button and you can toggle the image. It's the image toggle button, and you get the bright and dark pupil images. And generally we focus on this because this gives you almost all the information that you need to debug. We're a firm believer in letting you know what's going on. The only one possibility is if you do the dual glint in the off-axis light, you get the you've got twice the number of possible objects that would occlude your pupil. So again, you can see these glints here doubling up on the eyes. Again, if your head is like this, you're good. Control the light in the room without sound. So if the room has fluorescent light, which is quite common in many environments, there's no infrared in fluorescent light, and so it will have no effect. This image will look the same. This room is lit with LED light, so LEDs also don't have really any infrared light, and that's also very common now. The only one that might be a little problematic is incandescent lights, and those are the old light bulbs that heated up. They're now like illegal to manufacture, and so those are less and less common. But some old desk lamps, you might have an incandescent bulb. If you shone that in the person's face or you had it into the eye tracker, that might be problematic. If it's off elsewhere in the room, it should be fine. So you really shouldn't have to control the light in the room as long as it's not sunlight, with the exception of you look at this face, and if the pupils are very dim for elderly or very bright for children, then you might want to actually tweak them a little bit. So if you're in a lab environment, turn off a couple of the lights, or if you have the ability to dim it, that might help as well. So a couple things to try. And then for biometrics tracking, what I was gonna let's see. Okay, dial is pretty straightforward. You just move the dial 0 to 100%. For GSR, there's a wide range of baselines such that there really is no baseline. You can see numbers in the tens of kilo ohms to mega ohms. For some reason, I'm typically around 800 to 1.2 mega ohms of resistance. My hands are not that sweaty, but some people have much sweatier hands, and so this number is going to be much lower for those individuals. So there's no kind of baseline number for GSR. It should be, somewhere between tens of kilo ohms to mega ohms. What you're most interested in GSR is the change. So if you've seen in those police shows, they get the baseline, they ask the questions, what's your name, how old are you? And then they start asking the questions that cause stress. So you get a baseline, you watch a neutral commercial, and then you watch an aggressive commercial or something like that, and then you see how this responds. If I mentally challenge myself, I can see if I can change it. a bit of a parlor trick. This is actually something you can buy in mental health or some new age applications where you train yourself to still your mind and body. And by looking at this, you've got some feedback into what your body is doing behaviorally. But anyway, that's GSR. In terms of heart rate, you want to see, a pulse train, ideally. You want to see a heart rate. Again, people vary. Some people's baseline heart rate's 80, some's 40. If you see something in the 150s, then maybe that's an issue. But a modest line. The one trick on this, though, is if you've strapped it too tight, which I will try to do. Strap it really tight. No, I didn't just die. I've just strapped it too tight and cut off the blood flow. And not like my finger's going to go gangrene, but the signal is not coming through with enough intensity for us to track it. So the strap was too tight and I cut off the signal. So you want to strap it in to a reasonable tightness that gives you the signal, the little pulse train. Our system's not designed for jogging and action. A lot of heart rate and fitness sensors are for that, but for us, the Biometrics is more an add-on to eye tracking. So you're watching a video, you're watching a commercial. You can also get that signal added, and it's just in the gaze data feed. Okay, so that's tracking, and we're almost at the point of gaze. So the next step is calibration. So we've got the hardware in front of the system, we've got the participants sitting down, we've got the environment the way we want it. We're happy with our tracking, and so now we need to calibrate, and let's do a calibration. So we're going to do a 5-point calibration, and I'm looking at the dots. The dots go around the screen. And we do a quick check. And we're looking good. Okay, so that's calibration. It's a 5-point calibration. The end result is this little screen here where we can check our work. We can check how well the calibration went. When you calibrate your subjects, don't just calibrate and assume it worked. That's a very bad idea. You make that assumption, you do your recording, and then you realize that the calibration wasn't good and the whole thing was no good. You've got no good data. So when we do a calibration, I'll always say, okay, and I'll use my finger and point to the screen and say, okay, look here and look here and look here. Or I'll look at the top right one, look at the center one, look at the bottom left one. So I give directions and I'll do a visual check just to see if the eye tracker estimates are good. If they're not, I do another calibration. And in fact, I always do a second calibration for a first-time participant. If you sit someone down who hasn't done this before, eye tracking is new to them, it's all new. And so it's a new experience. When you're instructing them, they'll often look at you as you're giving, okay, look at these points. And they'll say, oh, okay, sure. Or they'll start talking, and the act of talking shakes the head. So during calibration, you want a nice still, just the eyes are moving. So what we suggest is that anytime you run a study and you're running participants, often this will be the first time they've ever seen eye tracking. Do the calibration, explain what's going to happen. You can explain while it's happening, and say, okay, let's do one more. Stop talking, let them focus on the 5 points. It's only, it's under 10 seconds of time. Just let them look at the dots, and then you can start talking to them afterwards. Don't keep talking through it. You're giving them a reason for them to look away from the screen. So do it twice. Once they're familiar with the process, and if they go away and come back, you can do it again. Once is enough, but we do suggest get them familiar with it first, then do it again. 5-point versus 9-point. So you've seen I've been doing 5-point calibrations. You can do a 9-point calibration. The end result is it's not that much better. You don't really get a more accurate result. You get a more robust result if some of the points aren't calibrated as well. But if that's ever the case, I suggest you just redo the 5-point calibration and figure out what's wrong. Is the glasses causing something issue? Is there something with the eyelashes? Figure out what's wrong. Don't just continue on. The 9-point just takes more time. If, let's say, the middle point here were to not work for whatever reason, you've at least got the 2 other points at the top of the screen that might assist in the calibration. But in general, we suggest 5 points is enough. You've covered the range of the screen, and if any point is not great, solve that. Get the subject a little higher, tilt the eye tracker, figure out why it didn't work as well, and then just redo the calibration. Real-time observation. So we highly recommend you have a dual monitor setup. So you have the participant who's going to do a study. They're going to look at something on a screen, give them a screen, and then have, in addition to that, a second screen attached. And laptops, you can easily put in a second screen, and same with desktops. And then take this image and put it on the second screen. So when you do the calibration, I'll move the calibration. Select screen. Okay, put the calibration on my screen over here. I have to move the eye tracker, but at any rate, you would be watching. So you can't see the calibration right now, but you would watch my eyes as I'm looking around the screen. I'm just kind of faking it here. And that will give you some feedback. Like if something weird happens and something stops working at a location, you can spot it. Whereas if you just are staring at this screen, you're not getting that additional feedback for running an experiment. You want your experiment to run as smoothly as possible. And this window gives you a lot of feedback on how it's performing. So we do suggest a dual monitor setup so you can watch what's going on. Do the eye tracking sanity check at the end. So do ask the subject to look at the points again to get a check for how well the calibration was performed. Biometric sanity check, again, you're going to wire the subject up and take a look at those numbers, make sure that this is a reasonable number, and make sure you can see the heart rate pulses coming through. You didn't strap it too tight. Children primates. Okay. And by all means, jump in if you have questions as we go. But so children, there's really interesting research done on nonverbal children. So children who haven't, are too young to learn to speak or haven't learned to speak yet. And then primates is not something we have any real interest in making the system work for. But in terms of calibration, there's one little thing you can do to make it work better for these 2 subjects. And you need the calibration dots to be attractive. What makes it a dot attractive? Motion, so the movement. So you'll see that our calibration has animations. It moves, it shrinks, it's got a number to look at. So there's a lot going on there to keep your eyes busy for the few seconds that it takes to get the calibration performed. Now that's when I can give you the instructions and say, look at the dot, and you're there. Okay, I look at the dot, I look at the dot. If you want it to work with children, here we go. Here, we'll do the song version. We have the ability to add a image and an audio file to each calibration point. So Now that is very annoying, but it's also very attractive as it goes through for someone who's nonverbal, a child. And you could have, a teddy bear, a banana, a clown. You change the images, change the sound. That was just an example of the various capabilities. So that kind of a calibration is useful for subjects who you need to give an extra motivation to be looking at the dots. Okay, so now with all of that, we have a dot on the screen. We have our point of gaze estimate, which is an XY coordinate. I will draw it here. So I've slaved it to my mouse cursor. And so we've got an XY value on the screen. Okay, so great. We actually have a little more than that. We have X and Y, but we also have some time metrics. So the human gaze is often, well, you can kind of split it up into different behaviors. And the two primary ones are fixations. So if I'm going to look here at the P, or let's say I'm looking at this picture here, I will look intently at it and my eyes are focused on it. And so I'm fixated on this. I'm looking at the details of it and processing that. And so that's known as a fixation. When I'm no longer interested in looking here and now I want to look down here, so then my eyes will jump down to here and I'll start looking at this. And so that jump is known as a saccade. So you have a fixation, jump, saccade, another fixation, and so on. So your vision is made up of a fixation and then these quick jumps. There are a few other eye movement types, smooth pursuit, and so on. The ones we're most interested in are fixations, and the saccade is really the jump. So really, we're mostly interested in fixations. So the fixation has an XY, like where am I looking? But it also has a start time. So when did I start looking at this? So with respect to the start of my, let's say, recording or experiment. And then for how long was I looking at this point? So, okay, I started looking here at time t equals 5 seconds, and I looked at it for 5 seconds. Well, that's a very interesting feature. I spent a lot of time looking at it. This one, I didn't spend anything, I spent half a second, and so that was less interesting to me. So the duration of the fixation is a valuable piece of information. And then you also have an ID, basically each fixation, it just increments by 1. So as you can actually get an order in which you looked at things. So this fixation was number 1, and I looked here as number 2, then this was more interesting than here, so this was 3, and then this one's number 4, and so on. So you have a sequence of fixations with the ID value. Okay, so that wraps up the first part of the talk, which is where you are looking. So we looked at the equipment, we looked at the subject, we looked at the environment, we looked at the image processing, the things we're tracking, pupil and glints, we did our calibration, and now we've got our point of gaze on the screen. So any questions on that? What's the difference between fixation and gaze? Sort of the same thing. Fixation is a more detailed word, which means the point that you're looking at. I'll do a recording and show you what a fixation. I'll show you visually what a fixation is, and then gaze is just kind of a general term. I'm looking around the screen. I'm gazing around, and so the word you'd use is fixation. What are you fixating on? That's got more specificity than the word gaze. I'll do a recording and then actually show you what that data looks like. Okay, so that's our point on the screen, or our fixation on the screen, and now we want to know, okay, what were you looking at? What was on the screen when you were looking at that point on the screen? So that brings us to our next tool. So this is the eye tracking engine. It's the thing that tracks the face and computes the point of gaze, and then it feeds that data to other applications. So this kind of generates the point of gaze information and feeds that off. we have an API, and many eye trackers have an API which allow you to get that data feed in real time. So let me run my little demo API. So this is just a text interface to the API, and our API just runs off these sort of XML strings, XML fragments, and so let's set sending data. Okay, so this is an example of a sequence of data being sent from our server, which is the eye tracker, and to a client. Most of you probably never be interested in this. Some people want to make their own application. So they want to make their own unique system that does something based on, for example, a gaze contingent display. So a gaze contingent display is a display that changes depending on where you look. So that's a unique application. And so you get this data feed from the server to your own application, and it has your X and Y. It has your start time of a fixation. You know, you can see me as I look across, there's another start time. So I'm looking at this start time, then I look over here to duration, and now you can see that number is going up 4 seconds. And now if I look to the next one, it resets, and I've got another fixation ID, and so on. And we've got a valid flag. So if I'm not generating data, there's no valid fixation, and now we're back to valid fixation. It goes 0 when I blink, and so on. So that's an API interface. What that means is there are many applications that can take this data. So we have one that we call analysis, Gazepoint analysis. But there are many others. Andrew uses, is it PsychoPy? Which one? I can't remember which one. There's a number of open source PsychoPy. So there's a number of open source data analysis, experimental tools that generate the display, record the data, and give you the analysis tools. You can use MATLAB even. This is just TCP/IP based interface, so you can get the data into MATLAB directly, or you can use one of these tools to log the data and then export it and get it into SPSS or MATLAB. There's PsychoPy. There's a large number of different clients which will take that gaze data and then allow you to do your experiments. So in this case, our tool, we have a few different modes. So we have screen capture, we have image, text, video, we have web browser, web aggregate, and mobile device. So these are the different media types that you might want to do an experiment on. So what's the difference? Screen capture is for dynamic content of any application on the computer. So let's give it a try. So let's make a new project. I think I already, okay, let's make a new project. New project. Let's make a screen cap PowerPoint. Okay. PowerPoint. So it's going to be a screen capture project. I'll say create slide. And let me just turn off this guy. And now you're seeing this picture in picture, and I haven't figured out a good way around this, but we're giving you a live feed of the capture. And what we're doing is we're capturing the screen that's doing the capturing. And so it does this picture in picture in picture in picture. That is okay. You really should be on a dual monitor. And so this actually goes onto the second screen while the subject then does their experiment. And now not only can you see the subject's face, so you can see if they start doing this, talk to you, you can say, oh, do you mind looking back at the screen? Or you also get the real-time gaze markers. So you can see that this is the real-time feed of where they're looking at on the screen. I think I may or may not have bumped the system or not calibrated it. So I'm going to calibrate one more time. Just don't want to do that. Let's do normal calibrations. talking during calibration, do a quick check, just kind of check the corners, make sure that they're reasonable, and that's all looking good. And so now I've set up my experiment. I'm going to take this to the other screen so that I can, I really want you to be able to see this, but I'm wary about changing my screen. Okay, I don't want to mess with Zoom, so I'm gonna move this to the other screen. So I'm gonna put it over here. And then what we're gonna do is I'm gonna start the recording. So okay, I'll do it over here. I'll start the recording. So now it's recording data. And what I'm gonna do is I'm gonna add a slide. No, I'm gonna make insert new slide. This is a new slide. I don't know what to put on it though. Maybe I can put an image. Where did that image thing go? All right, this thing. Picture. And no, I don't want that anymore. Okay. So I finished my experiment. I clicked stop. Again, this should have been on the second screen, which it was. So so the experimenter could run it. And now we're going to play that back. So here we have what we call a fixation map. Okay, I should describe what we're seeing. So we have a time slider, which is the duration of the experiment. We have a screen capture of whatever was on the screen at the time. And we have the gaze overlaid. And in this particular case, we're looking at fixation map display. And I'll talk about the different kinds of ways of visualizing that. And so here, I was looking towards the start button. Clicked it. And then so what you're seeing here is old data as well. So fixations occur and then content changes, and then you look at the new content. And so you need to, so this is all sort of historical data. And so depending on what was there, so once this is off the screen, then the data that was looking at that is sort of no longer useful. Then this little menu comes up. I start looking at the menu. I'm looking for the new slide button. It's not there. So it's actually behind here. So if we look here, I'm looking for the next, the new slide button. And so I'm looking for the button there. And so at this point, where to go? So I've found the icon. My cursor was over here, and now I'm going to come over and I'm going to click on the, Zoom is doing a overlay. Oh, I can move it. There we go. Okay, so then I click on new slide. The new slide comes up. I start doing a title, start adding some text, and so on. So basically, this is in PowerPoint, and all we're doing is screen capture of whatever was on the screen, and we can get our gaze overlay on it. And when I talk about fixations, you can see each one of these dots is a fixation, and it's got the duration of the fixation. So the bigger the dot, the longer I was looking at this. So I was trying to find which one of these is the add image icon. And when I finally found it and clicked on it, then I start looking at the next thing that comes up, looking for a picture to add, didn't find one, and then click cancel. So that is an example of a screen capture project. And that slide. So that's great for any application. So just some random application you have on the screen, your own custom application, content that changes and moves. What's problematic though is it's difficult to aggregate. So if you had 10 different subjects trying to make a new slide, they'll all do clicks at different times and different things will come up on the screen at the same time. So it's difficult to aggregate the data. And it's difficult to have one set of AOIs. So an AOI is known as an area of interest I might say that, let's see, here I'm going to add an AOI around these blocks. So I've now got a start point to the AOI. And then we'll do an end. So we've now got, I'm jumping around a little bit, but so that content showed up here and then disappeared here. So we can say, I never looked at that AOI, and then it shows up again at some point. So then it shows up again here. So I could make it show up again and so on. But for someone else doing this task, that would show up at a different point in time. So these time markers for the AOIs are not valid for the other subject. You'd have to have a new set of AOIs for that subject. So this is extremely powerful and useful for individuals. But when you're trying to group people together, you have to study them. You have to study the data set individually. You can't do them all at the same time. So that's screen capture. Okay, the next type of content is image, text, video, things where the program controls the display. So here I have one pre-made. These are just some stock content. So we have here text. We have here a Gazepoint advertisement, which is not real. It's just to show you a logo and a brand. And then we have a transition slide. So if you are interested in what people look at first, then if you have multiple images, the most interesting content in image one, let's say, attracts the eyes to the top left. When you start the next slide, you're going to be looking at the top left because that's where you were looking last. And so that might skew what you look at. And so in this case, having a center point brings the eyes back to the center. You flip to the next ad or image, and then you're now leaving from the middle. So the middle isn't the most attractive feature. It's just the starting point. And then you see where the eyes go first. So those are examples of images. So I'm gonna go back to the center, and then we have here a video. So this video will start and play back for 20 seconds. That's just some stock video that has some stuff moving around. I previously recorded something, so let's actually do a recording. We'll collect some data. So I'm going to run this experiment. It's not that long. Please observe the following images, and I'll look at the new image, Gazepoint, center. Kind of looking around, center point, video. And what I'm kind of doing for you, so it's not so boring, is talking while I'm doing it. So I'm looking at the graph. That's interesting. Yeah, the graph's going up. That's good for business. What that is known as is think aloud. So as I'm looking at the image, I'm thinking aloud. And that's a common usability tool. And so that's also built in. So you can actually run, I can't do it now because I'm already using the webcam, but you can actually turn on audio and video recording of a webcam at the same time. And you can get a little window like this up in the corner. And then you get the kind of mental stream of thought while the experiment is taking place. Some cases that's useful, and some cases it's not. So just another tool for usability. Okay, so now we've got 3 different people who looked at these sequence here, and we can look at them all at the same time. So if I turn them all on and we start to, and we go to analyze, black is a bad color choice, black background. Okay, so we all started looking kind of somewhere around here, and then everybody was kind of looking around, and then somebody started reading here, and then the other person's got to the please. And so Mr. Red read faster than the other two. And then Mr. Yellow is looking down here at the zoom. So the yellow was the one that just recorded. So when I put the zoom thing over here, you can see it. It ruined my recording. And now we can say something about what's going on from all three subjects at the same time, because they all saw this content at the same time. So let's see, in this ad, you can say everybody started at the middle point. That was the center point marker. Seems like most people looked here first. And then, so one person, two people went down here. And so now we can actually start running AOIs on content. So say logo or whatever you're doing. You know, if you're studying aphasia, people who see faces and not, you can have, you know, a left pointing face and a right pointing face. Whatever your experiment is, the why you're doing this is up to you. This is the method of display. So those are images, and then with video, again, you've got video content, and this content is now dynamic. So unlike text and images, this video has things that move. And so you need to keyframe these AOIs. So the map has a start time, and then we have keyframes, multiple keyframes as the map moves around the screen. And then eventually the map disappears at this point in time, and so on. So you can put your AOIs in the image, and then with those AOIs, you can calculate statistics of what happened. So how many people looked at it? When did they, on average, first look at it? How much time did they spend looking at it? Or how much % of time over the overall experiment did they spend looking at it? How many revisits, so how many times they look at it, look away, and then look back. How many times they click on it. So there's a number of stats that you can now get without you having to do the stats calculations. It's all calculated for you with AOIs. Now, on that topic, if we wanted to do the stats ourselves, you know, ANOVAs and so on, you're going to need to do that in your own stats package. And so for that, you can export the data. So you can pick all the different kinds of data, blinking, fixations, and cursors, the biometrics data, and so on. Oh, I should have done one biometrics. At any rate, so you export that as a CSV file. Let's open up CSV file. CSV stands for comma separated value. Does analysis export the AOI coordinates? That is an excellent question. Andrew's really getting me, and the answer is no, not yet. Let me double check that in a second. This is just the gaze data. So this is all the gaze data, and you can see all the different data records in CSV format. Now, one thing that has caused us a little trouble is in Europe, commas and periods are inverted. So in North America, the decimal point, the 0 point something, it's a decimal. In Europe, it's a comma. And so what do you call a CSV file in Europe? Is it a comma period value? Comma separate? No. Yeah. Do you have the equivalent of CSV, comma separated values? Because in Europe, if it's 0 comma something, tab separated, right? You can open this file in a different way. So you can convert you call it CSV, even though there's the commas and periods are inverted. At any rate, something for you guys to deal with is to figure that out. I'm sure it's a solved problem to get your data into Excel, except Excel is not that great for data analysis. So you probably load it into MATLAB or SPSS. Comma, yeah, exactly. Okay, so that's your raw data. You import that. You can run your stats. There's a field for the media. Each media thing has an ID, and so you can, like in SPSS, you can split that up into different blocks. So you've got the intro image block, and we have add one block, and so on. So that's how you do your deeper analysis of the data. What you see in here is a high level kind of basic stats on the AOIs and a visualization. To Andrew's question, let's see if it's in here. We have a start time and a duration. No, so we don't export the AOI values. So for you to do the mapping of gaze data to AOIs, you'd actually have to get the numbers from here. So here's the X, here's the Y, here's the width and height. All of our numbers are percentages of the screen, and that makes them insensitive to whatever screen ratio and pixel size and density you have. But it means you need to convert, if you want it in pixels, you have to take all our X numbers and times it by your width, and all our Y numbers and times it by the height. So if it's 1920 by 1080, you take this number times by 1920 and this number by 1080. So these are stored in percentages of the screen, which does make a lot of sense until you get to the very end when you really want it in pixels. So to convert it to pixels, you just multiply those numbers. What does every row mean? Okay, that's a good question. I'll get to that in a second. So there's your X and Y. What that doesn't give you is the interpolation. So you can see that this thing was keyframed over time. And so we do that interpolation in the program, but we don't export at each data point the X, Y, width, height, and so on. Couldn't figure out how that would be easily interpreted or taken in by the end user. So if your AOIs are static, you can just get the data from here. But if they're dynamic AOIs, then you might be dependent on our system for doing the calculation. What does every row mean? That's an excellent question. So we have a couple of different data files exported. So we have the data summary, and the data summary is the AOI export. So for each AOI, here we have the stats for each user. So user ID 1, 2, 3, 1, 2, 3, 1, 2, 3. So for each AOI, each user, we get the data records. And then this set of data is the average. So it's the averaged of all the subjects. And you might have 100 different well, 100 is a big number. You might have 10, 20, 30 subjects. And so this will be the average over all of them. So this is just for the AOI. In these files, so the user gaze data files, so let's look at all gaze first. What we have here is each row is one data sample, one call it, you can almost think of it as one image. So each image that's created here generates one data record, and that gets captured, transmitted, and then logged. And so each one of these is one record. So at 60 Hertz, you'll have every 16 milliseconds. So here it's 15.6, so 31 milliseconds and so on. So each 16.6 milliseconds, plus or minus a smidge, you get a data record. And so this is like all the data. It's all the gaze data that you have. What we find is most people are less interested in all the data. They're more interested in the fixation data. So if we look at this image here, let's do an image. If we look at this image here and we zoom to the end, so this is a 4-second image. And if I show 4 seconds of historical data to display all, so this is from start to finish. This is all of the fixations from 0 to 4 seconds. Then each one of these circles is one fixation, but this fixation here took 0.5 seconds. So this is 500 milliseconds of data. And at 16 milliseconds a sample, that's, I don't know how many, what's 0.5 divided by 0.016 number of samples, let's call it 20. So there's 20 rows that are, well, okay, let's go look. I don't want to look that up exactly, but basically, instead of having 20 records for that one fixation. We also give you a data file that is per fixation. So instead of every data record, we do it every fixation. So in this case, you know, we started at fixation 1, and then 2, 3, 4, 5, 6, 7, 8, 9. So there would be 9 rows for this image, which is add 2 for user 3, and I don't remember which one, what green was user 2, so wrong one. But anyway, each one of these fixations, so let's zoom it out here. So fixation ID, so we have fixations for add 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for this user, there was 10 fixations. So each row in this file is one fixation. Each row in the all data file is one data record, and many data records can comprise a fixation. That makes sense? That's a very common question. You know, what does this data mean? Another question we always get is, what do these rows mean? What does CX, CY? In the manual, in the Gazepoint API manual, each one of these records is described, and so you can get that through this one. But that's the difference between the rows. Okay, so we're nearing the end. Okay, so that was screen capture, whatever's on the screen. Text, image, video. Easy to aggregate because everybody saw the same thing at the same time. So it's easy to put everybody on the same image. I'm going to skip these and come back to them in a second, just so that we can talk about these different displays, just while I have this up. What we're seeing here is a fixation map. It's a map of the fixations over the image. So this shows people, they looked here, but they looked here because that was the marker point. That was the center point. Then they looked here, and you can follow their path around. So this is the order in which they looked, and you can look at the numbers. You can animate it over time to see the path in which they're looking. Like counting fixations. The stats in our AOIs are the most common ways you would look at it. So how long did it take you to look at an object? How long did you spend looking at the object? Those are the most important aggregations or statistics that you would have on content. Revisits is maybe less common, but you know, how long did it take you to notice it and look at it, and how long did you spend looking at it? So fixations will give you that information. A heat map does not give you that information. A heat map is just a visualization of where time was spent, and the hotter it is, the more time was spent there. Transparent. So heat maps are good for a quick visual impact of where people were looking. So we can say, yes, people did spend some good time looking at the logo down here. Nobody looked at the icon over here. So a heat map it's not a quantitative display. It's more just a visual impact. And that's similar to an opacity map. So an opacity map, it's basically just a heat map, but instead of colors, we're using transparency. And so the content that you can see is the stuff that was seen by the user, that the user spent time looking at, whereas the dark was not looked at. So that's an opacity map. And then a B swarm is just a single point in time. So you can see ... And that makes much more sense when you animate. You can see the flow of interest over time. It's like having a single fixation, but without the duration information. For 3 people, that's not very interesting. But if you had 50 people, you can imagine with 50 people, this ends up just looking like a big smear of data. And so the B swarm is a visualization that looks more sort of a data reduction that you can actually see what's going on. So that's the different kind of graphical visualizations. There's some settings, so like you can show how long, so what history of gaze. So right now we're at the 4-second mark of our 4-second display, and we're showing 1 second worth of data. So we go at 4 seconds, we go show 1 second of historical data backwards. So what we're seeing on screen is from 3 to 4 seconds where people were looking. So that's the gaze duration. And then the rest down here, these are visualizations for the biometrics, which are, oh, I should show that. Things like pupil size, so pupil diameter, that is a biometric signal. It's a signal that the user does not consciously control. It's just a thing that changes. It also changes due to ambient light and so on, and the brightness of the screen. So there are confounding factors to pupil diameter dilation. But you have pupils, you have heart rate, skin response, and blink rate. So these are sort of biometric signals of interest, and those are shown as line graphs over time. So those are just the line graph. It's a way of visualizing the data. If you want to do actual statistics to answer the question that your research is asking, you get that into your MATLAB or your SPSS and run your stats on it. Graphing, AOIs, we talked about exporting. So we already did exporting. We did the CSV image and video. So let us just wrap up with these last ones. So web browser. Open the browser project. So with the web browser, we have 2 kinds of web content. We have the web browser, which is basically the same as screen capture with a browser focus. So if let's turn that one off. Okay, and we have multiple screens, so you can pick which screen you want to. So it showed up on the other screen, but it's basically just a web browser, and you do screen capture of the web browser and do the gaze overlay. So it's the same as screen capture in that you capture the dynamics of web content, but then it's difficult to aggregate and make sense of multiple subjects. You have to analyze it sort of one at a time. We do have another web media type called web aggregate. And web aggregate, so some systems will have something like that. And what they are a plugin that is the browser itself. So now the browser is actually Gazepoint analysis. So it's actually Chrome under the hood, but it's actually the browser built into this program. And so my content, I'm going to look at cbc.ca. So let's start the recording. And so this browser is a very basic browser. I'm not sure why it's not loading. Okay, well, I pre-canned one. Maybe it just takes time. So this looks like screen capture. So my page is rendering, but we've actually captured the full page. So the full web page was captured in addition to the screen capture of the content on the page. So you can see that at the start, the page is blank. We hadn't rendered the page yet. Then as the page renders out, we start capturing the content of it. And my gaze now makes more sense. Stuff is now visible on the screen. And so I can start looking at headlines. I look at this video. And now I start scrolling. And you can see there's dynamic ads that are popping up. And as I scroll around, I'm tracking the scroll. You can see that okay. And then once the page is finished rendering, we take a screenshot of that. So now we have effectively a still image of the web page, and we can have multiple subjects who looked at the same page, and we can now then compare, okay, how long did they spend looking at, you know, this video box down here, and how long did they spend, you know, looking at the ads on this side or the ads on that side, or whatever media on that web page is. So it's sort of a hybrid of tracking the dynamic content with a video and then overlaying that video over the actual page. So tracking the scroll and so on. So this, in this example, worked on this page, but there are pages that it will not work on. The web is now so dynamic that you've got infinite scroll web pages. So how do you take a screenshot of an infinite scroll web page? You can't. And so the use case of this particular media type is limited to the pages on which it would work, and it won't work on everything. There are pages where you can reconfigure the page, and then of course that's not going to match between subject A and subject B. So it's for pages that you know, render to a fixed size. You could have multiple people watch that page. The page does not dynamically change itself around. And you can have videos that play, you can have content that pops up and goes down, but not that change the size of the image or size of the page. That was web aggregate. And then the final thing which I have is mobile device. Don't know if we have time. Do we have another couple of minutes, Chris, or is that you know, wrap it exactly on time?
Yeah, I think we are fine.
Okay, so it'll just be a minute then. So that is the last. So the last media type is mobile device. So we got a lot of interest in, you know, tracking, eye tracking on a mobile device. And so we created a system for that. And so I'm going to see if I can point down towards that. It might be that you just can look at me. I'll be looking sideways, and you can look at the screen capture. But basically, it's a holder for the mobile device. The mobile device is connected through the web to the eye tracker itself. And so it's its own eye tracker. So I'm going to switch eye trackers. So I've got two eye trackers plugged in here. And so now I'm looking at my mobile device eye tracker. I've connected. This is an Apple device. We can do Chrome and we can do we can do Android and we can do Apple. And so let me see if I can. So I click calibrate, and now I'm looking at the mobile device. The mobile device has its own calibration. It's the same calibration through the API. And then now I can't see what's on the screen anymore. So I'm going to start recording some data. And just I'll check my work. Maybe you can tell me, was that accurate?
Yeah, it's pretty good.
Perfect. Okay, so that's calibration on the mobile device. And now if we want to collect some data on that, we can. So tell me if I'm looking at the phone icon and the camera icon, FaceTime.
Yep.
So on that, we're already there. Let's go to Chrome.
Yeah, sorry for interrupting. So where is the eye tracker located?
So, okay, so that was, okay, let me just scroll down. Okay, so you can see that you've got gaze now overlaid on the phone. And what we're doing here is we have the eye tracker on this little mobile holder base. So it's an eye tracker that has a different focal length, which is hand distance to the screen. So you can put your hand on the screen, you can manipulate the screen, and if you're looking in here, which I'm not right now, you'll get the eye tracking data on the screen that you calibrated on. So if you rotated the phone, you would need to do the calibration again. So you can do it in portrait or landscape, one or the other. and the data feed comes from the Android itself, or sorry, this from the iPhone itself. So the phones will output the screen, which we then can capture. And so then once you've got that, it's effectively the same as the screen capture media, where you've now got stop that, where you've got the screen capture, except you're on a mobile device capture, phone camera, let's say FaceTime, and so on. Okay, so that wraps up the talk. It is now time for your own unique research. So that's just the bottom layer of the stack, and then your application comes on top of that. So questions? We're out of time, so we had some good questions as we went through.